We're going to do Physics 2, 2025 exams, Physics 2. This is the most commonly examined physics paper and arguably really the most important, demonstrate understanding of mechanics, all that good stuff. So this is the 2025 exam. We're going to be using the formula sheet, the resource sheet that's provided to students in the exam, most notably this bunch of formulae and equations that were given to students in the exam. And we'll also be using the Casio 9800 series calculator, the most common calculator used. So let's do it to it. So every year they have a kind of common theme, and this year the common theme seems to be rugby. And you notice that we have these grey boxes that's where it's covered up, presumably so it doesn't infringe on copyright. Anyway, let's look around. So question 1 is acceleration. We're told that a rugby player accelerates uniformly from rest. So that means that the initial velocity is 0 at a uniform rate of 0.680 meters per second. So A is going to equal that, and they run 22 meters. The 22 meter line is the first sort of line that would be between the try line and the 22. So this is going to be our D. D is going to equal 22. So now they say, how long did it take to run? How long did it take to run the 22 meters? Oops, you don't cross it out. So what are they asking for? They want the time. So which formula are we going to use? We're going to use the D equals VIT. The T is the time, plus half AT squared. We know what A is. We don't know what T is. We're trying to find it. We do know what VT is. It's 0. So this is going to go to 0. And we know that this is going to be 22. So 22 is going to be equal to half times 0.680 times T squared. And we're trying to solve for T squared. So let's do mathematics first. Mr. Casio makes his first appearance. So 0.5 half times 0.68, 0.34. So T squared is going to be 22 divided by 0.34. Here comes calculator again. 22 divided by 0.34 is 64.705. I'm going to go through these order places. 64.7059, and T is going to be obviously the square root of that number. So I'm going to raise that to the power of half, which is the same as the square root. And it takes 8.04, we'll say 8.044 seconds. And that's the first question. So now we're told that while stopping, a player runs into a tackle bag. So you must see in tackle bags, they're these big sort of foam bags filled with, but you run into them and you tackle them and they absorb all the punishment rather than tackling the player and hurting them. So while stopping, a player runs into tackle bag at speed V. Okay. The tackle bag compresses the distance X, so it's going to kind of like be a spring. So here we have the tackle bag when we start, and then when we hit it, it's going to sort of deform. And this amount that it's deforming is going to be X. And it's going to be kind of like a spring. So here's the tackle bag there. And here is our tackle direction. Assuming all the player's energy is transferred to the bag, okay, that's a big assumption, but go along with it. State and just what will happen to the distance the bag was compressed. So we're looking for the change in this distance that's compressed. If the player was moving twice the speed that they were before, So, in other words, if we hit the bag going at 2 meters per second, how is it going to be different than if we hit it at 4 meters per second? Okay, so for that, we need to work out what energies we're talking about. So when the player is moving, the energy that's going to be transferred is the kinetic energy, because that's modeled by half mv squared. Very, very important equation to know. And it's going to be converted, all of that apparently, into elastic potential energy, which is half kx squared, where k is a spring constant and m is the mass. So all of that is going to become it's going to move from kinetic energy to elastic potential energy, and we're told that all the energy is transferred. So a couple of things to work out. The spring constant, the change in the spring constant is zero. It's a constant, it's set. That's why it's called a spring constant, no matter how much we squish it. Also, change in the mass of the player is going to be zero. They're not going to be moving so fast that they start moving near the speed of light and start picking up mass, getting crazy like that. So we can pretty much cancel those out straight away. But let's kind of go. All right, when we double velocity, so instead of having V, we have 2V, and we put that in there. What's our new kinetic energy going to be? Kinetic energy is going to be half m double that velocity, or we have to square that. And that's going to be half mass or v squared. So what's the difference between this equation and this equation? Well, it's the 4. You're going to not double the amount of kinetic energy, you're going to quadruple it. It's going to be 4 times greater. So, 4 times the kinetic energy, how is that going to change the potential energy? Okay, well, we're going to have 4 times half times k x squared. So what's changed? Because this is a constant, half is constant and k is a constant, the new amount that is being compressed must be 4 times the initial compression. Okay, let's sort of set these to the EP before and the EP after. So half xk squared, compare that to 4 times half k nu x, call it xf, well, we'll call it nu there, squared. So the halves will cancel, the k's will cancel, because remember we said at the top here that k doesn't change. So the amount of the new compression is going to be 4 times the old compression squared. Okay. So when we take the square root of that, the new amount that's compressed is going to be equal to the square root of 4x old squared, which is 2x old. So the amount that's compressed new is twice what it was before. So we quadrupled the amount of energy, but that means that we're going to double the amount of compression. So the next question sort of wants us to consider a penalty shot. So take a penalty, the ball is placed on the ground, what's placed in the kicking tee, and kicked towards the goalposts. To take the penalty shot, to make the penalty shot, I should say, the ball must be over the crossbar, which is 3 meters, in height above the ground and 45 meters from where the ball is kicked. So it's a pretty long kick. 45 meters. It's a fair way, especially if you're out wide and you're aiming for a little target by the looks of it. Player taking a penalty shoots, penalty shot, kicks the ball at 25 meters per second. I don't know if that's fast or not. At 34 degrees to the ground. So it's projectile motion, question really in disguise. Perform appropriate calculations and decide whether the ball makes it over the crossbar before hitting the ground. Okay, so we're going to presume these on target. So projectile motion, we have to break it down into its component parts, and we have the vertical and horizontal. So let's do our triangle here. So this is 34 degrees, and the hypotenuse is 25 meters per second. The vertical velocity in y direction, and velocity in the x direction, you have to work that out. And it's really just trigonometry. So first thing we want to do is we want to make sure that this is in degree mode. So this is in degree. Set x down there. So let's do the initial vertical velocity first. So this is the opposite side. So we're going to use sine. So sine 34 is going to be equal to the opposite side over the hypotenuse side. I guess that goes well, the goalpost. So the vertical component is going to be 25, which is the hypotenuse, times sine of 34 degrees. And this we use our calculator. So sine of 34 is that. Multiply that by 25. So the vertical velocity is 13.9798 meters per second. 98 meters per second. And the good thing about this is when we know the vertical, we know that we use sine, it's going to be exactly the same. So the horizontal velocity going along the ground is going to be 25 times cosine of 34 degrees. So cosine of 34 degrees is that. We multiply that by 25. So it's moving along the ground. Its ground speed is 20.7259 meters per second. 40p. Right, now that we know that, we need to sort of work out what's going to happen. So the horizontal velocity is going to be exactly the same. It's not going to change. So change in velocity along the x-axis, along the ground, due to time is 0. So it's never going to speed up or slow down. It's going to, but we're going to presume that it does in this case. Going up, though, we have this problem with gravity. But first off, let's be a bit tricky. So if it's going along with ground here at 20.7 odd meters per second, how long is it going to take going at that speed before it hits that 45 meters? So let's go to the tables. For that, we have used either of these equations, because VF equals VI, and we know what VI is. Let's use this one. So this one would go to 0 because the acceleration is 0 in the case. So the distance we know is 45, and we know that along the ground it's going at 20.7259 plus 20.7259 divided by 2 times t. And now we know how much time it could take. So let's 20.7259 259 times 2 is that. Oh, we're going to divide that by 2, so it's kind of a stupid thing to do. And the time it's going to take is going to be 45 divided by that, 20.7259. So 45 divided by 20.7259 is 2.1712 seconds. Okay. Now let's look at the vertical component. So this, we are going to use this one here actually. So maybe we're going to use this component here to work out where it is at any particular moment in time. And we're going to set t equal to that. Okay? Now, what is a? Well, a is the acceleration from gravity. And that's in the opposite direction from where we started. Because if we're picking up in gear, that's our initial. So our acceleration is going to be minus 9.8 meters per second. It has to be a minus. So the distance at any time is going to be equal to the initial velocity. So the initial velocity going up was 13.9798 times time, which is 2.1712 plus half times negative 9.8 times 2.1712 squared. We have no unknowns. It's just a matter of crunching the numbers now. So 13.9798 times 2.1712 is 30.3529 minus, so it's going to, the minus is going to come up front here. So 0.5 times 9.5 times 2.1712 squared. It's all in one go. Minus 23.0991. So after that 2 seconds where it reaches that 45, so 30.3529 minus 23.0991 is 7.2538. Here we go. Meters in height above the ground, which is greater than 3 meters. So yes, presuming it's on target, it makes it. Now, we need to prove that it didn't hit the ground first, don't we? So for this, let's go back to this equation here and see if we can find where this equals 0, and that will tell us the first time it will hit the ground. So D is VT VIT plus half AT squared. Okay. And the initial velocity, VI, is 13.9798. Acceleration is gravity, so it's going to be negative 9.8 as given in the form sheets. And the distance that we want is 0. So in other words, when does it go up and when does it come down, which tune of 0? So for that, we're going to put this into an equation. So 0 equals 13.9798 minus times 9.8, which brackets t squared. There's a t here. And we want to solve that for t. Well, I'm not really bothered to do that straight away, so I'm going to use the equation. Here I'm going to use the polynomial solver, degree 2, so 0.5 times 9.8 times -1. It's a negative number, so negative 4.9. And it's going to be 13.9798. And the constant, there is no constant at the end, so it wouldn't hit the ground. There it starts at 0, so it starts at time 0, it is at the ground. So it's not going to hit the ground until 2.853 meters. So the vertical distance equals 0 at 0 seconds when you kick it, and at 2.853 seconds when it hits the ground. So in other words, it doesn't hit the ground. I guess when it says proof it doesn't hit the ground. So they're trying to say that it didn't sort of go like this and sort of bounce along and bounce over the goalposts. Because they want to count, it has to go over on the full, I think. It has to go over on the full, doesn't it? I've never seen it happen, but I think it has to go over on the full. So that's our proof.
So a player from part C replaces the ball with another ball from a different manufacturer. The new ball is heavier, so it has a heavier mass. The player kicks the new ball towards the post so that it leaves the ground at the same speed, I think the same velocity they mean, and the same angle as before. Ignoring any effects from air friction without using calculations, compare the path of the new football to that of the original. Well, this is in fact...
No? I'll throw it open. Coventry City last won the FA Cup in what year? No, well, I'm not surprised you didn't get that. It was, in fact, a trick question. Coventry City have never won the FA Cup.
A trick question. If the velocity is the same and the angle to the ground is the same, it will have the same trajectory and it will land in the same place. The reason being is that gravity paradoxically ignores mass. It's not related to mass. It accelerates all objects of any mass at the same acceleration. So it will have the same trajectory and land in the same place. So there you go. Maybe perhaps you would have had to have hit it with a greater force in order to get the same velocity, but once it's got that velocity and after it's left your foot, it's going to move in exactly the same way. And just like that, we're on to question 2. So an 80 kg player moves at 4.30 meters per second. Calculate the player's momentum and give the correct unit. Well, momentum is given as mass times velocity, which is going to be 80 kilograms. It's already in SI units, times 4.30. It's already in meters per second. And we grab Mr. Casio. Mr. Casio comes out and he works it out for us. So 344. So 344. Now what's the unit? Well, momentum doesn't actually have a name for a unit. So you've got two choices for momentum. I guess you could say kilogram meters per second, or the other way is newtons per second, but that would probably be the best one. Explain why using momentum to study collisions is more useful than using kinetic energy. Well, the main things are that momentum is always conserved in any collision, whereas kinetic energy is not. the energies and losses converted to different forms. The conservation of energy applies to all collisions. So using momentum, we can convert that to energy. We can convert to energy. Wow, what happened there? We can convert to energy using conservation of energy, and we can better explain what's going on in any collision, not just elastic and inelastic. What else? Kinetic energy is only conserved in, now I have to think, perfectly inelastic, perfectly inelastic collisions, and there's really no such thing as an absolutely perfect elastic collision. Okay, momentum always has the same form, and it also is a vector, so we can see where things are going when we analyze momentum. We can't do that for energy, because energy momentum P has a magnitude and a direction, so it's much more useful when we're trying to construct what's happened in a collision to use momentum calculations rather than energy calculations. The mass of the All Black scrum is 883 kilograms. There's 8 forwards in a scrum, and they all weigh 883 kilograms in total. The Argentinian scrum is 850 kilograms. As the scrum is set, the All Blacks move forward at 0.354 meters per second, and the Argentinians move forward at 3.78 meters per second. So in other words, the All Black scrum is larger, but it's moving slower, and the Argentinian scrum is slightly smaller, but it's moving larger in the opposite direction. Who is going to win? Well, okay, let's have a look at it. So we've got our two scrums. We've got our front row forwards, locks, flankers, number 8, and we have the other guys here. Their locks and their flankers and number 8. So the Argentinian squad is pushing that way, in that direction. The All Blacks forward pack is pushing in that direction. Which one is going to win? Well, it's going to be a pretty simple calculation, actually. We're going to take the Argentinian, because it's left to right, as the positive direction, and the All Blacks as the negative direction. So the momentum going from left to right in the positive direction is all Argentina, and that's going to be 850 kilograms, so it's already in SI units, times how fast they're moving, 0378. And that's going to be minus what the All Blacks are moving in the opposite direction, which is 883 kilograms times 0.354 meters per second. Which one is going to win? Well, Mr. Casio comes out. So 850 times 0.378 minus 883 times 0.354, and we see it's positive 8.718. Okay, now what does that mean? That means, well, the All Black set piece coat, since they got rid of Steve Cron is, of course, one of Razor's mates from Canterbury. All of the All Blacks coaches seem to be Razor's friends from Canterbury, and that seems to be the only qualification. And the All Blacks are being put to shame here by a smaller pack. A smaller, less experienced, less coach pack. So the momentum is 8.718 kilogram meters per second in that direction. So how fast is it going to be moving? Well, the way it's going to be moving, we're going to be looking at the total mass, and that's going to be both of the packs. So that's going to be 850 kilograms plus 883 kilograms, and it's going to give it a 1733 kilograms. And we know that momentum is mass times velocity. So the mass is that one there. We know the momentum, that's going to be 8.718 in that direction. And let's work out the velocity. So the velocity is, we're going to divide both sides by m. So the velocity, and it's going in that direction, is going to be the momentum, which is 8.718 divided by 1,733 kilograms. I've no idea what that is off the top of my head, so Mr. Casio comes to the rescue. 8.718 divided by 1,733. So it's moving very, very small. So 0.005 meters per second in the direction Argentina is pushing the once great All Black board pack. So I guess Razor will need to try to do what he did with the Canterbury Crusaders to make them such a good team, and let's poach other players from other unions and rely on really, really friendly refs. Oh dear, yeah, you can't do that in international rugby. I guess we're stuffed. So now we're told that the ball comes out of the scrum and a player sprints towards the line. The player is tackled and brought to a stop by colliding with thick pads, cushions, that are at the bottom of the goalpost. Being anywhere near a rugby field, you should know what these look like. Explain how having these pads help protect the player when they collide with the post. Well, the main reason that it protects is that it extends the collision. It extends the collision. I have to remember to write legibly. When I mean that, I mean the time it takes to go to zero velocity. Okay, so it minimizes the impulse to decelerate. Okay, so the change in momentum, P, is over a longer period and therefore requires less impulse to stop. Okay, so that means that the collision is dissipated in a much longer time. Okay, so if you jump off a building, when it's not the fall that kills you, it's the sudden change in momentum when you hit the ground. But if you hit a barrier very slowly and it slows you down gradually, the impulse and the change in momentum that your body will experience will be less, because the time it's kind of used up over that time. It's why crumple zones and cars are so good, they increase the time that the car takes to crumble, meaning that the car takes the energy rather than the person that's driving the car that takes the energy, which is a bad thing. And just like that, we're at question 3 now. So when warming up, players run up the stairs. Calculate the work done by a 68.3 kg player who runs up the stairs once. Now, there's a trap here to sort of say, okay, well, they run 35 meters. No. This is all that matters. It's change in height that we care, because work is the change in energy. So we're converting kinetic energy into gravitational potential energy. So change in gravitational potential energy is mg. G is gravity, change in height. And the work energy concept means that we can do that. So the mass is 68.3. The gravity, acceleration from gravity is 9.8. The change in height is 14.1 meters. They're all in SI units. So we can proceed with our calculations. So 68.3 times gravity, which is 9.8, times the distance, the vertical distance that we've gone up. So 9437.7 joules. Another warm-up activity is short sprints. During one sprint, the 68.3 kilogram player accelerates from rest to 7.52 meters per second in that length of time. Calculate the average power produced. All right, there's a couple of ways we could do this using force maybe, but really we're going to look at change in energy. So it's the energy that we're really caring about is the kinetic energy when we start versus the kinetic energy when we finish. The kinetic energy when we start, so let's sort of call that the kinetic energy initial, is going to be half times mass times the velocity squared. But when we first started off, the velocity was 0, so it's going to be 0. So the kinetic energy that we have at the end here, when he's going that speed and that much mass, we'll get to the time in a second, is going to be this. So it's going to be half times the mass, 68.3 kilograms times 7.52 squared, comes Mr. Casio. So half times 68.3 times 7.52 square equals 1930.2 joules. Not bad acceleration there, I've got to say. Okay. We could work out the acceleration and then work out the force, and then force times distance, but this is going to take us there much quicker. So now, if we want to work out the power, the average power, then capital P equals the work done, and that's the work done, it's in joules, over the time it took us to do it. So it's going to be 1930.2 joules divided by 4.35 seconds. Calculator time. So I've already got that in there. So we're going to divide by 435. Whoops. No. 4.35. And we get 443.95 watts. And I guess you could up that to 444 watts if we're really going to this one decimal place. 444.0 watts. So now we get to the torque questions. While waiting to play, two players sit on a uniform bench. The bench is 621 newtons. So newtons is the downward force in this case, otherwise known as the weight force. And the bench is 621 newtons and is 3.21 meters long. A 669 Newton player sits to the left of support A. So let's call this player player 1, and we'll call this player 2. And a 769 Newton player sits 2.4 meters to the right of support A. Okay. Add label diagrams to the above diagram to show all the forces acting on the bench. Well, the first one is from this player 2 here, and this player 2 is this 796 player, isn't it? 769 Newton's player. This player here is 669 Newtons, and then we're told that the bench itself is 621 newtons. So that's going to be there, and it's going to be 621 newtons going downwards. So there is going to be a force from B pushing upwards, the reaction force, and there is going to be a force from A pushing upwards to support this mass. We know there must be, because of Newton's laws, opposite and equal reactions, that the force A plus force B must be equal to these three forces. So 669 plus 769 plus 621. Otherwise, the bench would be floating off. If FB and FA were greater than the forces pulling it down, that means that there would be a force pushing it up, and the bench would rise off the ground and float away. If these forces were greater, then it would sink into the ground and then stop, but then there would be resistance force in the ground. So these equal and opposite forces have to exist in order for it to be in equilibrium. And the 621 has to be in the middle, the center of mass, because that's where all the mass is concentrated. Right, so what are the forces on B? So forces acting on B in the clockwise torques are going to be this person here. So this is from the fulcrum at A, and this person is 0.24 meters times 769 newtons plus the pulling down of the bench there, and that's going to be 621 newtons times 1.345, because it's halfway between these two is 1.345 meters. So let's look at the forces on A now. And the forces on A that are anti-clockwise torques. So that's going to be just that player that's to the left of it, which is 669 times 0.110 meters. This player here in this very small distance, plus what is an FB, times 2.64. So now we can look at the clockwise torques must equal the anti-clockwise torques. So that means 184.56, which is what this is, plus 835.245 newtons, which is what this was, and that's going to be equal to 73.59 plus force that's being pushed up at B times 2.69, which is the distance between them. So when we add these together, I'm not going to use the calculator because it's just going to be tiresome. This is one exception where I actually did the numbers beforehand. Plus 2.69 FB. So force in B is going to be, take that away, 1019.805 minus 773.59 torques. Divide that by 2.69, and that's going to give us whatever is FB. So 1019.805 minus 73.59 is that. Divide that by 2.69. So 351.75 newtons. Okay, but we know that A and B here have to add up to 2059 newtons. 2059 newtons. Okay, so if FB is 351, the force that's on A plus 351.75 equals 2059. The force on A must be this minus this. 2059 minus 351.75, well, 170725 newtons, which makes sense because they're all sort of surrounded by A. A has most of these weights around it, so it makes sense that that has a much greater carry. So if FA is 351.75 and if B is 351.75, then FA must have more because there's more things putting more pressure on that point there, that fulcrum. Just before the players enter the game, they use one more warm-up activity where two players hold hands and move around a circle at a constant speed. Add an arrow to the figure B to show the direction of the acceleration of one of the players. Well, it's going to be from there to the center. It's centripetal acceleration. The acceleration is always from the outside to the center. So now we're asked to explain why they move at a constant speed, yet they're accelerating. Okay, well, they're moving at a constant speed, but they're not moving at a constant velocity. And remember, there's a big difference between speed and velocity. Speed is just how fast you're going. Velocity is how fast you're going in a direction. The velocity is changing because you're changing direction. Okay? And a change in acceleration, a change in velocity over time is acceleration by definition. So acceleration, you can accelerate one of two ways. Either you can speed up, slow down, or change direction. So when you're moving in a circle, you're constantly changing direction. Therefore, your velocities change even though you haven't sped up or slowed down. And if your velocities changed, there must be an acceleration. That's that. So that's the end of that exam. It was a pretty simple exam. Any bits you wanted me to go over, I'm perfectly happy to go over that. Next off, I'm going to be doing the electricity exam, and it looks like I'm not going to be able to do all of it because by the looks of it, they've kind of done this to it. There's a lot of grey spaces that are blocked out, but we'll give it a go. So I hope you enjoyed that. All the best.